Hello everyone, in this video tutorial we are going to simulate membrane dialysis process. We will be considering two cases, one steady state simulation and another transient simulation. So in the steady state setup, uh, this is the membrane module. We have two membranes, membrane 1 and membrane 2. The dialysate enters at this site, which include the toxin or any species. So and the permeate enter at this site. So at the dialysate move, species transfer from the dialysate to the permeate site through these two membranes. So this is the first simulation that we are going to perform, and these are the results that we will obtain from this simulation. The concentration profile in the feed site, in the membranes, and in the permeate site, and these are also the concentration profile as a line graph in the at the different section of the membrane module in the feed membrane 1, membrane 2, and at the dialysate site. And this is the concentration profile at the exit of the membrane module. So we are going to uh, develop these results from the steady state simulation. Similarly, we will also perform the transient simulation where the dialysate returns to the mixing tank, and the residence time in the mixing tank is 100 seconds, and this is again feed to the membrane module. So we will do the simulation for 1 hour. The simulation, the process time will be 1 hour, and we will see that how the concentration changes in the tank as the time progress. So open COMSOL Multiphysics. So the COMSOL is open now. Click on the file, click on new, click on model wizard, click on 2D, and add the physics. So click on chemical species transport, double click on dilute transport of diluted species, and similarly click on fluid flow, click on single phase flow, and add the laminar flow. Now click on study and select the stationary study and click on done. So first I have to add the parameters that are used in the simulation. So click on the parameters, and you can load the parameters directly from here. Click on this load from file, and click on this. Okay, just import these parameters. Uh, these parameters can be found on the Google Drive, the link of which is given in the description. So I will just go through these parameters. This is the permeate. Sorry, this C1 in is the dialysate input concentration. This is the permeate input concentration. KS1 is the partition coefficient at dialysate site. KS2 partition coefficient at the permeate site. K12 is the partition coefficient between membranes. Similarly, this is the input velocity of both permeate and dialysate. These are diffusion coefficient at the dialysate site, membrane site, sorry, the permeate site. This is diffusion coefficient of membrane 1, diffusion coefficient of membrane 2. These are the WCH is the width of the channel, the permeate channel, and the dialysate channel. This is the thickness of membrane 1, thickness of membrane 2, and this is the length of the module. So now click on the geometry, right click on the geometry, select rectangle, and I will just write WCH plus WM1 plus W underscore M2 plus W underscore CH. Width of the permeate, the dialysate channel, width of first membrane, second membrane, and width of the dialysate, the permeate channel. And this is the length of the module is LM. So build all objects. Okay, this is not visible. However, you can see from here that this rectangle is formed, which is up in this. So I will now just add the layers to this rectangle. So click on this layers, and here enter WCH layer 1. If I click on build selected object, sorry, and select, check this layers to the left and build all objects, so you can see this layer is added. If I write WM1 here and click on build all objects, you can see another layer is added, and also add another layer, build all objects. Okay, click on zoom extend. Now click on the form union and click on build all. So we have created our geometry. However, this is not visible. For that, go to the definition, click on view, click on axis. From view scale, select the automatic and click on update, and then click on the zoom extent. So this is the geometry of our system. Next, click on the material, or just you can also add from here. Click on material, click on add material, and add water here. So search water, and I will add this H2O water liquid. Double click on it. So the water is added to our system, all of the domains. Now go to the transport of diluted species and click on transport properties 1, and I will call this as a dialysate. Okay, this domain 1, and here user velocity field, select this velocity field. Actually, this velocity will be calculated by this laminar flow model, and that velocity field will be used by this uh, uh, that velocity field will be used in solution of this equation, which you can see here, equation. So you can see the u here. This is the velocity field. So this velocity field will be calculated by this laminar flow. This is actually coupling of the momentum and the mass transfer. So back to the dialysate, and enter ds1 here. Okay, this is the dialysate diffusion coefficient. And now right click on the transport of dialysis species, click on transport properties, call this membrane 1. Okay, and just select membrane number 1, and here, okay, I will now here the velocity field is 0 0 because there is no convection in the membrane. So only diffusion occurs in the membrane. So write this diffusion coefficient dm1. Again, transport of dialysis species. This is membrane 2. Just select membrane. Sorry, select select. This is membrane 2. Sorry, membrane 2. Select the second membrane, and again the velocity field is 0 0, and here enter dm2. Okay, again right click on the transport dialysis species, click on transport properties, and here enter permeate. This is the permeate site. Select the permeate, and now again I will select the velocity field here, and here I shall write ds2, which is the diffusion coefficient of the permeate, right? So now you can see dialysate ds1, membrane 1, okay, and dm1, membrane 2. Here we have written dm2, and permeate. Here we have written ds2. Now we have to enter the boundary condition. So for that, click on the physics, click on the boundaries, and click on the inflow. So this is the first boundary condition, the dialysate input, and this is C1 in, which we have already defined in the parameter section. Similarly, again, click on the boundaries, click on the inflow, and click on this boundary, and I will write this as C4 in. Okay, this is the permeate input concentration. Okay, now we have to define the outputs as well. So the outflow, this is the first outflow, and the second outflow. Okay, we also need to define the partition coefficient boundary condition, that what is happening at this boundary, what is happening at this boundary, and what is happening at this boundary. So for that, go to the boundaries, click on the partition condition. Okay, so at this boundary, the partition coefficient is a case1. Okay, and just click on the reverse direction. Okay, you know that partition coefficient is defined as the concentration in the membrane, the ratio of the concentration in the membrane to the concentration in the dialysate. If I don't click on this reverse direction, that would mean that partition coefficient is defined as the concentration in the dialysate to the concentration, ratio of the concentration in the dialysate to the concentration in the membrane. So that's why you need to click on this reverse direction. Now again, click on the boundaries, click on the partition condition, select this boundary, and put K1 2, and again reverse direction. Okay, another partition condition which is defined at this boundary, and here write case 2. Okay, this I will not click on the reverse direction because The partition coefficient here is defined as the concentration in the membrane to the concentration in the permeate. So now we have defined everything related to the mass transport. Now I will. So we have defined everything related to the mass transport. Now I will click on the laminar flow. Okay, and as you know that there is no laminar flow here, no flow here. There is no convection in these membrane. So I have just deselected those membrane, and I have selected only domain number 1 and domain number 4, which is our permeate and dialysate side. Okay, now uh, click on boundaries, click on inlet, and at this boundary the velocity is a u naught, and again click on inlet boundary. At this boundary, this is also the velocity is sorry, the normal input velocity, this is a u naught. Okay, uh, and again click on the boundaries, click on the outlet. This is outlet 1, and also add outlet 2. Okay, so we have defined everything related to the laminar flow. Okay, here it in the transport dilute species in the inflow, just change this condition from concentration constant to flux tank words. This is more suitable boundary condition, and this also changes to flux tank words. Okay, now we have defined everything related to the mass transfer and to the momentum transport. So now we are going to mesh our geometry. So click on the mesh, right click, click on map, and again right click and click on distribution. So select these boundary 1, 4, 7, 10, and 13, and click on predefine. Here write 30 and 5. Okay, and if you click on build arm, so it has actually divided this whole geometry in 30 elements, and the ratio between this element and the last element is a 5. Okay, so that means that this is 5 times you can say larger than this element. Again click on right click on map, click on distribution, select these, sorry, select this and this boundary, don't select this one, and click on predefine 20 and 5, and click on build all. So you can see we have further divided this geometry, and similarly at another one, and click on predefine. This is 20 element ratio 5, build all. Again distribution, these two boundaries, and predefined, and this is 20 and 5, and click on build all. Okay, now go to the study and just click on the compute. Okay, so this is the concentration profile. Just click on this concentration, and we don't need the streamline, so we need the streamlines. So this is the concentration, and you can see that as the dialysate moves forward, the concentration decreases, while the concentration here increases in the permeate side. We will see this more clearly in another result that I'm going to generate. However, just call this as study concentration study 1. We call this concentration 1 study 1. Okay, and click on results, click on 2D plot group, and call this as concentration 2 study 1. Okay, and right click on this concentration and click on the surface. So surface 1, and again right click on surface and select selection. Okay, select this one. Okay, and you can see that here we only the concentration profile in the dialysate is now visible. Okay, you can just right click on surface 1 and click on duplicate. So surface 2, this is surface 2, and at surface 2 click on selection, click on this button and select this domain number 2, right? Again, you can right click on the surface 2, click on duplicate, and in the selection just activate this, deselect second domain, select third domain. Okay, and again another duplicate, and click on selection. You can select this one and deselect the third one, right? So now these are the concentration profile. You can see that as the liquid move forward in the dialysate section, concentration falls, while the concentration increases at the permeate side. This scale is for the dialysate, this for membrane 1, membrane 2, and this one for the permeate side. Okay, now go to the data sets. Oh, sorry. Yeah, data set, and click on this cut line 2D. Okay, and here enter 0 and WCH static 2. I will explain this. W underscore M1 plus W underscore M2. Okay, and this is L underscore M by 10. Also type L underscore M by 10. If you click on plot, you can see that a line is drawn here. So the first point of this line is a 0 and Lm by 10, right? 0 and Lm by 10. The second point is a Lm by 10. So this is Lm by 10. The length is divided in 10 parts. Lm by 10, and this this is the x x-axis, x point, and this one is the y1, right? So we have plotted a line here. Actually, I want to see the concentration profile here, 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 and across this module. So you can add additional parallel lines. For that, just click on this range button, and here right we want to start from L underscore M by 10, like we want to start from here, and Lm by 10 increase by Lm by 10, and stop at 9 steric, so 9 steric Lm by 10, sorry. Click on add. So I need to write Lm here. Okay, so, and this is range Lm by 10, Lm by 10, and non-static Lm by 10. If I click on plot, so you can see that these pair lines are drawn here. Now I want to see the concentration profile from here to here, from here to here. So for that, click on the 1D plot group, and right click and add line graph. Okay, and from select the cut line 2D one. Okay, and click on plot. So you can see this is the concentration profile, the membrane side, sorry, the feed side. This is the concentration profile in the membrane 1, 2, and the dialysate at a different section. So what are those different sections? Just click on the regions here, so you can see that which lines belong to which distance, right? So you can see here at distance 1, this is the concentration profile when distance is 0, at distance 0.1. This is actually concentration profile at in the very bottom, Lm by 10. This is 2 static Lm by 10, 3 static Lm by 10, and so on. So we can also just plot the concentration at the outlet. So for that, click on the results, click on the 1D plot group, and right click and add a line graph. So I want to see concentration profile here, and sorry, just activate this and then select these boundaries. This is the outlet. Okay, and just click on plot. So this is the concentration profile at the outlet of the module. Thank you for watching, and we will simulate the transient simulation in the second part of this video.